All right, so now we're starting derivatives of our parametric equation. So we're going to do it two different ways here just to kind of introduce these derivatives. We're going to first rewrite it in terms of y and then take the derivative as we normally would. So you can see this is our function here, and you can see that it is increasing from here to here. So our curve is increasing. We have a vertical tangent right here. And so we'll discuss all of that as we move through these videos. But right now it's just a derivative. So if we do what we did before, we're going to remove that parameter. So we have x equals t cubed. So if we take the cube root of both sides, we get that for t. We can then plug that in. So you can already see a direct substitution here where t cubed is x. So t cubed would just be x, and then our t cube root of x. So now if we rewrite these as general powers, we can then take the derivative. Rewriting it would give us 1 plus and then 1 over 3 x to the 2/3. So that is our derivative. And so you can see we have a square on that x, which means this is always positive. So it's always positive. It's always increasing. And right there is our vertical tangent at x equals 0, x equals 0. All right, now let's try our derivative in terms of t. So we're going to go back up and grab our functions, x equals t cubed. So I forgot to write them down here. That would have been smart, right? But I didn't. So we need to go back up and grab them. Y equals t cubed plus t. Now, if we take our dy dx and we do a little changing of variables, so our dy dx is our y prime of x. We have dy dx, and then we're going to put a dt dt here. And then we just do a little switch. So we're going to switch the dx and the dt at the bottom. And so now if you take this one and do the reciprocal, we end up with it at the bottom and this one at the top. So we end up with y prime of t and x prime of t, dy dt and dx dt. So we're going to use those notations to start with, just so that we get used that we're taking the derivative with respect to t. This would now be 3t squared. 3t squared plus 1. So all it really is we take the derivative of the x and the derivative of the y. We put the y on top, the x on the bottom, and that is our dy dx. So the y goes on top. And now we want to match what we have up here. So we have a derivative in terms of in terms of x, and we have a derivative in terms of t. So if you think of our curve here, right, you've got an x and a y that we're getting the slope of the tangent at. But we also have that parameter t, which gives the x and the y. So we can use it as well to tell us what the slope is. So if I were to plug the t in, I would get the same slope here as plugging that x value into our derivative that we have as well. So both of them would give us the same slope. We would get our vertical tangent right there, and we would have increasing all the way through this entire curve. So to show you this, what we're going to do is take that t now and do a little substitution back into the x. Because remember, the parameter t gives us our x. So if you were to plug in the x value or the t value, you get the same thing. So if you remember, our t is equal to the cube root of x. So if I plug that in, let's do a little simplifying first though. 3t squared over 3t squared would be 1. And then we get 1 over 3t squared. So now if I plug it in, we get 3 cube root of x squared, which would be 1 plus 1 over 3 x to the 2/3, which is what we got for our y prime. So you can solve for x and then take the derivative in the old way, or you can do it now with the parameter t. And I would use this way for the entire course, because what we're going to be doing now, not for the entire course, the entire section, because we're going to be using the t now and asking for what value of t will we get a horizontal tangent or a vertical tangent, or when do we have what values of t do we get concave up and concave down. So we'll be doing second derivatives as well. So that's our first intro to derivatives with parametric functions.